So just to introduce myself, my name is Phil Goff. I'm a product marketing manager here at Flex Power Modules. And I'll be joined on today's session by Ola Hellgren, who is Director of Marketing and Product Management within the organization. And just a moment here, just to introduce you to us as the company, if you're not familiar. Up until 6 years ago, we were part of Ericsson, the telecommunications company, Ericsson Power Modules. And so we have a long history here in terms of telecom and also datacom, or the ICT industry, when it comes to board-mounted DC-DC converters. More recently, we've introduced a wider range of products for the industrial segments as well as the rail segments as well. We do consider ourselves a technology leader in DC-DC. It's what we've done for decades, basically. It's really what we focus our efforts and R&D efforts on. We have an impressive track record in digital power as well. We've been working with PM Bus and digital solutions for, again, well over a decade, and very much focused on data center applications as well. The total product portfolio consists of power interface modules, isolated and non-isolated bus converters, and non-isolated point of load converters and VRMs. So it's really a system approach from start to finish when it comes to the DC conversion. And also just more recently, we very much specialize in tailor-made custom solutions for the key customers in this particular segment of AI. So with that short introduction, I will hand you over to Ola Hellgren to take the first part of the presentation.
Thank you, Phil. Let's jump into it and take a look at the agenda. We start with some generic words about the artificial intelligence and machine learning segment, the fundamentals of this segment. The second thing is driving forces. Who is behind the decision-making, how this system will look like? Who will drive the innovation in this segment? The third thing is the architecture connected to power and also the products we have on hand right now. And then what comes next, the generation after the existing one, the projection of products for the next coming 2 years. A sum up and then question and answer. And please do not forget to fill your questions in the form. So, looking at the definition of AI, I stepped into Wikipedia and was searching for a definition of artificial intelligence and found following: the ability of a digital computer or a computer-controlled robot to perform tasks commonly associated with intelligent beings. Ability to reason, discover meaning, generalize, or learn from past experience. I think we all have some knowledge about artificial intelligence and have looked into some of these abilities. The gentleman on the right-hand side, John McCarthy, was a professor at MIT, and he invented or defined artificial intelligence. That happened already in 1955. So soon 70 years ago, and that was much earlier than I thought. He also defined a language, a programming language named Lisp. That happened in 1958, 3 years after defining the artificial word. So this is not a new innovation. It has been with us for, I said, almost 70 years. So if we look at the market as such, the past 2 years and the projection for the next coming 3 years is a growth of approximately 30%. If we compare that with the datacom business over a larger number of years, there we see a growth rate of perhaps 2, 3, 4%. So this is extensive in comparison with the growth of the market over long term. One of the other interesting things in this is the number of applications using AI today. We have a couple of samples on the right-hand side of the slide, a number of companies and a number of applications. We find the things we think we will find, like search engine, chat robots, and things like that, connected to the big datacom companies. But we also find Tesla with autonomous driving car and so forth. We find companies like Adobe, desktop publishing type of program as Photoshop and Illustrator. I think that if we will look at a similar chart in a couple of years, the number of applications using AI in some way will probably be 10 doubled or not even more. So we have seen growth in this, and we see an explosion in use cases for AI. So what is the things that differ in the AI application versus other datacom applications? Well, I would say that it's how the system is built. In AI, they are using both CPUs in combination with other type of processors like GPUs, TPUs, ASICs, FPGAs, ARM processors. In most of the other applications, you're using one type of processor, but not in AI. AI also, there is a structure of how you build these data centers, and they are talking about 4, 8, 16-way servers, and we will see in the next coming slides how things are built to generate a fully modular design. But first, we look at the power per rack. If I rewind the tape and look 10 years back, we were talking about 2 kilowatts, 3 kilowatts, something in a rack in a typical data center. Today, we are looking more at 12 kilowatts, 14 kilowatts in most of the applications for data centers. But AI, we have a projection to reach 100, 200, or even 400 kilowatts in a single rack. So you could imagine how much thermals and how to dissipate this heat and the management to do that, challenges to manage these type of power levels in rack. But it is an extensive growth in kilowatts per rack. So let's take a look at how some of these things are built. And to understand that, you also need to understand who is driving the things. Well, Open Compute Project, that's an innovation platform. It was invented in 2011 by Meta, Facebook at that time, Intel, Goldman Sachs, and Rackspace. And today there are a huge number of companies that have signed up for some type of membership connected to open compute projects. The vision from OCP is we believe that an open sharing ideas, specification, and other intellectual property is the key for maximizing innovation and reduce complexity in tech components. So, in other words, the more companies that pitch in with innovation into this, the faster the development will be, the faster we will reach these 100 or 200 kilowatts in a single rack. And also, that will be a platform for several vendors doing the same thing. So from a sourcing standpoint, it will be a robust platform to use because you have different choices. And that will also keep the cost in control. So sharing openly will provide a good platform for technology jump and also support in manufacturing and so forth. Then, as I said, let's look at how the architecture is built. OCP has defined the architecture and it's built in different layers. On the right-hand side, you see a GPU, CPU, something with a large heatsink. They are then placed on this OAM board, which is the accelerator module board. And we were talking about the 4, 8, and 16-way servers. And as you can see, this is an 8-way server. The OAM board is then placed on a universal baseboard, and those are placed in shelf, and the shelves in a rack, and the racks multiple in a row. So it's a very thought through modular design, how things are built, and this is driven by the OCP. We have some products that belongs in this area. And we have the first step converters, which is the BMR 330. We also have the second step converters, which is the 510. And Phil, you will tell us a little bit more about the products and the performance of those.
Thank you, Ola. Yeah, let's take a look at some of the different power architectures that are employed in this area for AI. You touched there, Ola, on the first stage conversion and second stage conversion. And if we take a step back, actually, one of the things that we've seen really sort of grow in popularity as the power levels have increased per rack is the change from a 12-volt backplane to a 48-volt backplane, or nominally 48 volts. It's typically in the range of 48 to 54 volts, somewhere around that. And that increase by 4 of the supply voltage decreases obviously the current by 4 and the losses by 16. So it's a huge benefit for the server manufacturers, the AI applications here, to move towards this 48 volts. And as I mentioned at the start of the call, obviously our legacy, our history is in 48 volts. So we have a lot of knowledge and capability in this area. And the typical conversion stage in the first step is to convert down to an intermediate bus voltage that is suitable for the customer's application. Typically, what we've seen in the datacom world is a 4-to-1 conversion down to 12 volts. There's some legacy requirements there from PCIe and from different memory requirements, etc. But in the AI world, there's more flexibility here. So there's actually the ability to remove the isolation from the first step converter, which improves or enables us to improve the performance and power density of the device, and also remove the regulation. So in this case, the 48 volts that's being supplied by the front end rectifier is very well regulated. So the DC-DC converter itself does not need to be tightly regulated. So this bus voltage, for example, could be operating from a 40 to 60 volt input and give a 10 to 15 volt output, but nominally it's 12 volts on a 4-to-1 converter. There are other ratios available, and we'll touch on that as we look at the next slide on our available products. So this example is an 8-to-1 ratio where you have a 6-volt intermediate bus voltage. That bus voltage is then distributed to the second stage conversion, which is to go down to the core level voltages. And there's different approaches there too. So we have the lateral power delivery solutions. So Ola already mentioned the BMR 510 in that case. This is one of our latest voltage regulator modules. But also more and more now, we're looking at the vertical power delivery solutions as well. So actually taking the power distribution network path much shorter, physically locating the power supply directly underneath the processing unit. And here we're talking about hundreds of amps going up to even 1,000 amp plus for the peak current requirement. So taking a look at a bit more detail at the products in this area, what we have is basically the BMR 320 as one example of a released product. This is an 8-to-1 conversion product. It's 40 to 60 volt input, 5 to 7.5 volt output, nominal 6 volt at 48 volt in. And it's a 400 watt rated device in a package measuring just 27 by 18 millimeters. Efficiency typically is in the range of 97.6%. And as I mentioned, this is one of the products that is currently already released, and you'll find details of that on our website. The next product in that type of area is going to be the BMR 321. And you see this is sort of slightly longer, slightly narrower solution, but we're going up in power now to 750 watts. 1500 watt peak capability, so it has an ability to provide peak power, and the efficiency is being improved to over the 98% level. And this is the first product really that's been driven specifically to target the OAM standards, the OCP accelerator module standards, to facilitate higher power in a longer, narrower package. That product will be available in the first quarter of next year, and we can share information with you if you're interested in that at this stage. Then looking at a couple of 4-to-1 ratio solution products, we have the BMR 313, which is again 4-to-1, so it's a 10 to 15 volt output, nominal 12. And this product delivers 1 kilowatt of continuous power and a peak power rating of 3 kilowatts at an efficiency level typically of 97.3%. You'll notice the package size here, 23.5 by 17.9 millimeters, or 0.92 inch by 0.7 inch. So exceptionally small package for such a high power density product. There is a sibling product to that as well in the BMR 314. This is a lower power rated device. It's 800 watts continuous and 1500 watts peak. Key differences between the products here are the switch technologies. So in the case of the BMR 313, we are using GaN switches, whereas in 314, we're using the more traditional silicon transistors. So we're able to get a higher power density from the 313. On the second stage, we touched on the BMR 510 already. So this is basically taking in as its input the output of the first stage converter and giving the final stage conversion to 0.5 to 1.3 volts programmable, or in the case of the BMR 511 from 0.5 to 1.8 volts. And these products, both of them can deliver 80 amps of continuous current and up to 140 amps of peak current. And the main difference between the two designs basically is, well, mainly it's the heat dissipation technology. So you see here on the BMR 510, it's designed for topside cooling in that the main smart power stages are mounted on the top side, designed to be connected through a thermal interface material to a heatsink or a liquid cooling system. Whereas the BMR 511 is inductor on top. The main switching, the main smart power stages are underneath. You can't actually see them, but they're located on this PCB. And that's designed to be pulled down to the customer board to dissipate the heat. Because of the differences in mechanical layout and makeup of the device, you see some benefits in efficiency actually on the BMR 511. So it is even higher efficiency than the BMR 510. But really it depends on the method of cooling that you have as the customer. Moving on a little bit to what's coming next. If we look forward and look at some of the developments that we're going to be pushing through in 24 and even 25, you'll see some of these devices that I've already mentioned. But for example, the BMR 510, the existing variant does not have any output capacitors mounted on the unit. That's expected to be delivered by the customer, very, very close to the GPU or ASIC or whatever is being powered. But we are developing a solution which has a number of output capacitors pre-mounted to the VRM. So again, to reduce the amount of board space needed as much as possible by the end customer. That will be released by the end of this year, that variant. Also coming through in the second quarter of next year, we have the next generation of the BMR 313. So this is the 3 kilowatt peak rated product. And here we're making a number of changes to this to both improve the efficiency of the device still further, but also improve the cost to performance ratio effectively. So, as the volumes are increasing, there is a demand and a need to reduce cost as much as possible as well. So this will be the next generation of BMR 313 coming next year. The BMR 322 is a slightly higher powered rating variant of the BMR 320, and we're going from 400 watts to 500 watts, and again in this 8-to-1 ratio product. And then finally, we're looking at various different ratios. So we've talked about 4-to-1 and 8-to-1. They're the sort of most popular ratios that we're discussing at the moment with our customers. But there are different ratios of interest to optimize the system level efficiency. 5-to-1, 6-to-1, 10-to-1, and even 12-to-1 are being requested. And so we are working on topologies that can offer very simple and easy switches to these different input to output ratios. And the power levels, of course, will be dependent on those ratios. So that's why it's shown here as an X kilowatt or a TBD kilowatt rating. Finally, then, in terms of the next products coming through, we've talked about vertical power delivery on a general level. And you'll see here in this slide, there are no part numbers listed. And the reason for that is that each and every one of these is a custom development, basically. So we are working closely with our key customers in these areas, those customers that demand the benefits of vertical power delivery, mounting the module directly underneath the processor, improving the power distribution networks by reducing the resistance, inductance, etc., and also thereby improving the transient performance of the modules as well. And also, of course, freeing up space on the top of the board. So reducing or increasing the power density even further and reducing the space needed on the top side of the PCB. In this case, basically what we're doing is we are using multiple stages of our two-phase and four-phase approach modules and creating multiple phase solutions. So in some cases, 16 phases, some cases 24, 20, 32, even up to 48 phases. And these also can be single outputs. They can be multi-outputs, like 3, 5, or even 7 outputs, for example. So a lot of the activity in terms of our product development right now is in this area. If you are interested in that, then please do reach out to us after the webinar and we can take further discussions with you. So just to sum up, some of the key points that I would bring to your attention here, obviously, higher conversion efficiency and power density are being really pushed hard by our customer base. The products that we're developing now are incredibly high efficiencies, exceeding 98%, and exceptionally high power densities. You know, some of the peak power capabilities are exceeding 15 kilowatts per cubic inch, so it's incredibly high power densities. And also the benefit really for us and for the customer is that the supply voltage is changing from 12 volts to 48 volts. And I don't think that's the end of it. As Ulla mentioned earlier, the power levels per rack are going even higher, 100, 200, even 400 kilowatts being touted at the moment. So we may even see the 48 volts transition in the future to high voltage DC, like 200 volts, 400 volts, 800 volts. So there's all sorts of potential movement in that area going forward as well. Of course, with that increase in power density and increase in power usage, cooling is a massive issue. And direct-to-chip cooling is very common right now. Moving forward, things like immersion cooling are gaining further ground. Some issues with regard to environmental sustainability on the two-phase, but on the single-phase, still very much in discussion. And so our modules, of course, we have to design our modules to be optimized for top-side cooling, for example, bottom-side cooling for low-profile rear board-mounted modules. I touched on this as well, but removing the isolation and regulation is improving the system efficiencies and reducing losses. And that's something that we've changed over the last couple of years to develop more and more solutions in that area. And also the requirements of these systems for higher continuous power, but even higher peak load requirements and transient loads as well. So moving to very short duration, but high peak current requirements and power requirements. So with that, we're going to wrap up the call for today. We have here on the slide just some touch points for you to go for and look for more information. The best place to go is our website, flexpowermodules.com. On there, you'll find a whole host of different information like blogs and articles and flyers of interest for AI specifically, where you can define and find out what products we have to offer. If you're interested in talking further with us in terms of vertical power delivery or any other area that you might be interested in terms of our product portfolio and your requirements, then you can drop us a line on pm.info@flex.com. And with that, I will open it up now to the Q&A session.